Good morning, everybody. Let me introduce you Dr. Umberto Straccia. He's a senior researcher at the Institute of Information Science and Technologies of the National Research Council of Italy, ISTI-CNR, at Pisa. He received a PhD in computer science from the University of Dortmund, Germany. His current research interests include logics for knowledge representation and reasoning, semantic web languages, fuzzy logic, machine learning, and their combination and application. He's in the top 100 of the Italian computer scientists. He's an editorial review board member of several international journals, including Fuzzy Sets and Systems and the International Journal on Semantic Web and Information Systems. He has collaborated in the development of several tools for fuzzy ontologies, editors, and reasoners, and this research is indeed related to the topic of today's plenary talk, fuzzy and annotated semantic web languages. Welcome.
Thank you, Fernando. First of all, I thank you that you are here at this morning at 9 o'clock sharp. And for the others, okay, they missed my talk. Okay, so in case you are interested, you can download the slide from my homepage. And I have there also an accompanying paper, you can get it from my page, where I describe the technical details in case you are interested in the theory, which is all behind here, a kind of summary, and all the bibliographic references. This is the overview of my talk. I'm not going to touch all of these arguments deeply. I just run over them because I don't have that much time. I start very softly about some philosophical questions, whether, as I'm dealing with fuzzy stuff, I don't know whether you know about it, so I just pose you some questions that you can try to answer during the night, during next days, during your life. Okay? So, what is vagueness? We start with very simple thing. First of all, do vague concepts exist? First question. Well, once you see them, when I explain you what they are, you will discover that most of concepts that we have in our mind are vague, and very few of them are not. So, to start it very easily, I kindly ask you to answer with a very simple question. What is this picture about? People from machine learning try to tag them with labels. It's not easy, I mean, to understand what this strip is about, what this thing is about. It can be a square, can be me, my wife, or just an abstraction of a very adventurous trip during the going through Iran to Uzbekistan with a motorbike or whatever. Can be many things, not necessarily here. But what the point is, what means aboutness? Can you define what aboutness means? Or can you define what is relevant to this image? Okay. So, what is a vague concept? A concept is vague if you cannot define it precisely. There is some ambiguity behind there. So, the aboutness of a picture. What is a tall person? What is tall? Can you give me a definition? Can you say when a person is tall or not? Or even more provocative, can you train a learner to say whether a person, given his features, is tall or not? What is a high temperature? A nice weather? Or, as I told, an adventurous trip? Okay? What is a characteristic of vague concept? That they are subjective. Each of us has a different, slightly different definition of the notion of tall person. And the definition are typically, or the notion is context dependent. A high temperature has a certain meaning if it deals with weather. It has a different meaning if I'm talking about water. Okay. Given that we more or less have an idea of what vague concepts are, next question is, what are vague objects? Do they exist in reality? Or has vagueness only to do with some abstract level? Question, do you see here a vague object apart from me? this one, the dunes. Can you define the border of these dunes? You see, we will have difficulties here. What are dunes? Okay, try to a heap of sand. How many grains of sand are necessary for a dune? Okay, anyway. Or, far from us, the sun. What is the sun? Can you define the border of the sun? This is a picture of the sun, you see. This is what we call a vague object, essentially. So an vague object essentially is lacking of a clear identification, like the cloud, the dunes, the sun. And what happens is that they have an identity relation, which is just, they are reflexive. Everything is identical to itself, and otherwise we have just some similarities between them. There's nothing else we can do. So a vague statement, then, is a statement that involves vague concepts. I love to be here. This is a vague statement, because it involves a vague concept, which is loving. Okay? And a characteristic of vague statements is that they are not entirely true or false. They may have intermediate values of truth. So a statement is true to some degree. And we use it everyday life. So now you try to go through your dictionary that you use in your natural language and try to understand how many concepts or items that you find in the dictionary are vague, most of them. Okay? Here's an example that shows you where vagueness comes in. For instance, if you would like to have a multimedia information retrieval system, this is ideal. Yeah? Here, if you have some objects and some classifier identifies these are Snoopy, these are Woodstock. Here you have background knowledge, no? Snoopy, and Snoopy is a dog, and so on. And then you would like to retrieve here image regions which are about animals. You get the ranked list. The ranked list expresses you the aboutness of the object related to what you're looking for, animals. Humans tend to make the things easier and put sharp boundaries around the vague concepts, like here. United States, they said, okay, humid area, blue. This is a humid area. Are we sure that this is exactly the boundary? This is artificial. Why is this point over here red and not violet, for instance? It's both. This has to do with by us. They decide that given certain features of the air quality, they decide whether the air that we currently have is good or not good, and so on. And the difference can be very sharp here. They say, okay, if it is above 74 micrograms per cubic meter, then it's bad. Here we have 75 and flashes up red. And what does happen? The traffic is stopped. I mean, why? Just one digit above the limit? It's nonsense. But this is how we do it. Okay, there are other cases like TripAdvisor, they do exactly the same thing. So, next point is to people that are not aware about the difference here involved between vague concept and exact concept is that they think that everything has to do with an uncertainty. This is not exactly true because there is a big difference between what is called vagueness or fuzziness and uncertainty. And now I try to give you an explanation about that. Essentially, when we talk or you talk then about uncertainty, you have to keep in mind that when you have uncertainty, essentially a statement is either true, completely true, or it is false. But you don't know exactly which of the two states are the case. And so you are guessing or say probably it is true. That's the way you talk. But the statement has to be true or false. ISTI here deal with statements that can have an intermediate value of truth. So it's completely different. It is orthogonal. For instance, here, it will rain tomorrow is an uncertain statement because I don't know what happens tomorrow, but it will either rain or it will not rain. So I talk about probability, okay? On the other hand, vague statement is when I cannot exactly establish whether it is true or false, and I have intermediate values, like heavy rain tomorrow. Why is this vague? Because I have heavy, the concept of heavy, which is vague, is graded. Here is an example of what can happen in a weather forecast. In the US, they define the rain, let me check. Okay, 0.5 millimeters. So if it is 0.06, then you have, like here, rain falls at the rate of 2.6 or less, it's light rain. Above 2.6 or 0.7, moderate rain. So in the weather forecast, they say moderate rain if you got 2.7 or more. Otherwise, it's light rain. So it's quite sharp, right? So we can do it a little slightly better and define functions like this. So we put here .5. So light rain goes from here to here. And if you have 0.7, 2.7, then it's a little bit right rain, but it's already a little bit moderate rain. So you get the idea that it's graded. Okay. You can also combine the two things. You have uncertainty and vague statements, like here. There will be heavy rain tomorrow. So I don't know what will happen tomorrow, so I have uncertainty. And also, I don't know exactly what is the definition of heavy rain, which is graded, so I have combined them. This is a vague, uncertain statement. So, okay. Just an overview about vagueness. So how is this dealt with formally? The inspiring part is mathematical fuzzy logic. So it's a logic, which is classical logic, but in which statements can be graded. So I'm not going exactly in all the detail, but a typical set, just remind it, you can see it as a set in which either an item belongs to the set or it does not belong to the set. So you get the value 0, it does not belong to the set, it's the value 1, it belongs. In fuzzy set, you generalize it. You get the degree between 0 and 1, okay? Interestingly, one has figured out that good functions to define the membership are these 4. This is called trapezoidal function, triangular, left shoulder, right shoulder. And most of the time, you can define everything through these functions, these sets. You can even partition your domain, usually in 5 categories. Very low, low, fair, high, very high. If you think about, most of numerical domains can be partitioned, or it has even been shown that humans tend to partition in 5 categories when they have a graded scale. You can partition in this way, or you can even be more clever using clustering algorithms that arranges the shape a little bit. So there's plenty of work here. Fuzzy set has been invented in 1965, just as I remember. Okay. I would like to try to skip this. Essentially, in set theory, you have extended the notion of intersection, union, complement, and so on to more general functions. And these are called norms. And here, in fact, you can define many possible alternatives for intersections. The typical one is like the minimum as intersection, maximum as union, 1 minus for the complement, but it can even be more complicated like Jugasiewicz, in which he defined these functions. The important point is there are infinitely many options to define the union and complementation and intersection of sets, but it has been discovered, it is a very important result, that any possible choice is a combination of these 3 functions. Can be no alternative. So this is interesting, theoretically. Okay, and in fuzzy logic, what one does, we take a sentence, first order logic, and attach to it a degree. And this degree states that how much the sentence is true. So rather than either true or false, you get the sentence is true to, say, to some degree, .5, .6, .7, and so on. So essentially, a fuzzy station is made in this way. This is a first order formula, and you have a degree. And this means the degree of truth of this sentence is at least R, where R is a value. And then you build a machinery that allows you to reason with these degrees, okay? That I didn't show you. I don't show it to you. Okay? It's too complicated for now. Now, this basic principle has then, later on in the time, essentially by me, migrated to semantic web languages. Let me assume that you know a little bit about semantic languages. Let me call that there are two main representatives, which is OWL and RDFS. So there has been a generalization of these languages to deal with vague concepts. Okay? So there are two representatives, like say RDFS and OWL, and there is a third one, RIF, okay, which has to do with logic programming. They have a little bit more difficulties there with rule-based languages because there is no yet a standard except Sphere. Anyway, RDFS, very short. You have triples, subject, predicate, object, like Umberto born in Zurich, very easy. Now you can define classes, relationship between classes, and so on. The important part is that you have 3 dialects in OWL, EL, QL, and RL. Essentially, they distinguish between the operators that they have. They have different expressivity. This means different computational complexity. Essentially, the program runs faster or slower depending on the constructs that you are using. And RIF is a rule language. There are many others right now. Unfortunately, they cannot agree on a common standard so far. Okay. Of course, of all these languages, there is a logic behind, formal logic behind. For instance, RDFS has intentional semantics. The logics behind AL2 are description logic, and in RIF and RULLM, the logic is essentially data log, or currently data log plus minus. This is this object, so in case you are interested in. And now I show you very fast how we can generalize these languages to deal with fuzziness. Okay? We start with something simple, which is RDFS. So you take a triple, attach to it a degree. Like object 01 is about Snoopy to degree .8, and this degree is given by the classifier. Easy. And then we can reason about that, exactly like we do it with RDFS. We can also query it. I can show here, look at the formal type like this. I'm looking of objects that are of type sport car, and they get a score. X has a price, Y, and the overall score is given by the score of being sport car and the cheapness degree of the price. So what I'm looking for is essentially I'm looking for cheap sports car. And I get a ranked list, okay? And this is different than, for instance, SQL or Sparkle, where you get sharp answers. You get an answer, it's not a ranked list. Here we get a ranked list. This is an example for multimedia retrieval. Again, here you get, you are looking for objects that are about animals, and you get a ranked list of that, okay? One you have seen in RDF, we attach a weight. We can generalize that by attaching something else in order to generalize the label that we attach to it. Not necessarily only a number, but we can generalize it to so-called annotation domain that allows us to attach a degree of truthness. Here we can attach a time stamp or an interval saying when the statement is true, let's say from today to tomorrow, this statement is true. So we give even a timestamp, time interval. We can attach to it a provenance label from where I have gathered the information and reason about it. I can also attach to it different domains like trust to establish how much I trust into the statement. And I can make very complex expression, RDF construction, like a certain country is dangerous during 75-83 with degree .8 and trustness 0.6, depending on the source from which I gathered the information. And then I can reason about it. So this is much more expressive than current RDFS. Okay, here is the formal definition of annotation domains that generalize what I've talked about. So I'm not going into it. You can see the definition in the paper. So this is RDFS. And about description logic, it's essentially the same. In description logic, you take a statement like this, which says that the individual I is instance of a class C to degree n. Pretty simple. And then you can also establish a weak subsumption relationship in class inclusions, like the class C1 is a subclass of class C2 with a certain degree. And I will show you an example later on how I generate automatically this kind of relationships, the graded relationships, okay? Concerning fuzzy owl, one can do something more. One can define explicitly the definition of young through functions. I can have a modifier, which are this object, very. So I can take a vague concept and modify it, saying very young, or very, very young, or slightly young, and so on. I can have, well, several other things. I don't want to go inside it. And here is an example. Here I define a minor is a person whose age is below 18 years, or maybe it's a strict 18 years. And then I define a young person. A person whose age is given by this function, which means essentially below 10 years, you are definitely young. Above 30, you are definitely not young, so I'm not young. And in between, you get the grade, depending on your degree of your age, okay? So depending on your features, you get the degree of youngness. And you can also define like the notion of heavy rain. It's rain and it has a precipitation rate given like this. So I get the degree. Whenever I have a day with a certain amount of rain, I get a degree of being heavy rain. At the same time, I can have a degree of being moderate rain. So they are not in contrast each other. Okay. We can do even something more. We can have aggregation operators, which allows me to define a good hotel like a combination of being expensive and luxurious, or giving more importance, to mere weight to luxurious hotel. Okay? So it's very expressive right now. And I can make like before, pretty simple queries, or like here, trying sport cars, which are cheap. I can definitely define it in this way. Okay, there are currently several applications using OWL, fuzzy OWL, let's say. Okay, and I've seen papers about multimedia information, propaganda systems, image interpretation. So image interpretation is different from image retrieval. Here you try to interpret what's in the image, so what the image is about. Ambient intelligence, we have about ontology matching, matchmaking, decision summarization, or we have also robotics. So we have had a case in which people try to use our system to send a robot underwater to inspect a shipwreck, and application in machine learning. Okay, these are some examples. This is funny. Matchmaking. You can use fuzzy OWL for automatically figure out what is the best agreement between a seller and the buyer. Essentially here, you want to buy a car, you express your preferences. Of course, you are not sharp. Let's say you want to spend at most 10,000 euro, but you can live also to spend with 10,100 euro. Of course, the seller the more discount it gives you, the less he is satisfied, and then you try to figure out what is the compromise, and you figure out it's around here. This point is called Pareto optimal solution, and you can define it. I mean, you get it for free when you use fuzzy owl statements, okay? This is the encoding, very simple. And then the system says, okay, please sell it at 31,250, because then both are maximally satisfied. Okay. This is an example of learning. Essentially, in this case, we had a case of TripAdvisor data about hotels in Pisa, where I'm working. And we had a big ontology about meaningful entities in the town. And the question was, what characterizes good hotels according to the visitors of Pisa? So we take the data from TripAdvisor, the judgments, define some things, and then what we got is interesting, one of these rules. So the important point is that these rules not only allow you to classify a new hotel, but allow you also to interpret easily the classification rule. Here, essentially, it says that, okay, if it has amenity babysitting and the price is fair, then this is a good hotel. And you got also the degree to which this statement is true. Okay, there are plenty of such rules that you get. And here is the definition of being fair here. The price is in between 68 and 112 euro, and so on. So this is also a side effect. Okay. There is also the possibility to use protégé to define your fuzzy ontologies. So there is a plugin tool that allows you to define all the stuff, and so you use protégé, and then it eases you the work in definition of your fuzzy statements, specifically fuzzy ontology. Okay, again here there is the possibility to generalize the whole to annotation domains, so include trust degrees, time stamps, and so on. Last part, there is the third category, which has to do with logic programs. So this is the rule language section. Essentially, you take a rule like this and allow to attach to the relations a degree, okay, S1, SK, which say to how much this relation is true, and then additionally allow also to combine these degrees with any arbitrary computable infinite time function. If it doesn't work, doesn't compute the result in finite time, then it doesn't make sense for us. I mean, from a computer scientist point of view. Okay? So essentially, you take the truth values of all the relations, combine them through the function f, and then say this is the result. Okay? This is roughly the idea. This is a simple example. Typically, you have a database. You have some simple rule here. It says that my first preference is having I'm looking for cars that have a price, and the price has to be a left shoulder function. Then I have a second preference, and then here and then this, I say that I combine these two preferences through a linear function, giving more preference to the first preference, so about the price, here the kilometers. And then at the end, you get a ranked list. And the major problem here is that you don't want to have a list of 1 million of items, but just the top K, where K usually is 10. Okay, so this is an additional problem. Okay? Currently, there are a lot of systems around for rule language, like Sphere, Dalderog, RuleML. In some cases, you can simulate the fuzziness within them as long as they provide arithmetic functions. If they provide arithmetic functions, then I can simulate the fuzzy part. Okay? Here again, you can extend them, and that's good. Conclusion. There are another 200 slides for the conclusions. Okay, so essentially, I tried to give you a short overview about fuzziness within semantic languages. Fuzziness is related to vague concepts and vague classes. And I showed you how one can incorporate them into semantic web languages. Okay, and this gives you more or less the picture of the current state. Green means done, red means to be done. Unfortunately, it's prevalence of Red in mature systems. Concerning inference algorithms, we are better, in a better shape. More difficult is query answering. I'll show you why later in a second. For instance, here, this is an emerging field. So can you imagine to have a functionality in current system that says visualize roads in which many of the recent car incidents involved severely injured people? Can we do that? No, not yet. But it could be a natural question. I mean, whenever people from a municipality would like to take action about a dangerous road, he has to define what dangerous road means for them. 5 incidents, 5 deaths, 6 deaths, 1 death, and so on. So here we have many, it's vague as well, vague concepts like many, recent. What does it mean, a recent car incident? 1 month ago, 2 months ago, 1 day ago, again. And severely injured people. What is this again, the definition for injured people, severely injured people. So in the literature, one more or less knows exactly in fuzzy logic how to deal with that in principled way, but currently it's very difficult to formalize them in current languages like Sparkle. Because they are not tailored to address that right now. So this is what I'm going probably to work on for a while. And visualize is also an important part, how you visualize that. What do I mean with that? You are going to show just a segment of a road. Where does the segment start? Where does the segment stop? Okay, this again shows you that we are most of the time just approximating what should have been done. It should be a flow, a graded flow of colors, let's say. If red is very dangerous, then we go from green, slowly we go to red, and then decrease again. This is what humans do usually, but not what computers do. Okay, that's it. Okay, question?
Thank you very much for your talk. Now we have some time for questions or comments.
Thank you for a very interesting presentation. I think that in the concept you presented, the fuzziness measure is independent on the subject. For example, if you set recent weather, then it is something else than recent climate. Yeah, we understand what about we talk about recent, but here the recent is quite independent. Recent is just a function. No?
Well, I told before that it's very subjective and context dependent. So here recent refers to car incidents that refers to a time period that belongs to our daily life, let's say. So, which means a matter of days, a month, and not a matter of hundreds of thousands of years.
Yes, but if we define the function of recent, that we will have different functions.
Exactly.
For okay.
In fact, what I missed when we define practically, when we define an ontology, let's say our dictionary, and we define toll, we don't define toll generally for everything, but we have a label that tells me where it applies. So toll hike, toll, or let's say small in terms of height of a person. So there are different definitions of tallness depending on the context they are, which means essentially you have different labels that you attach to the same notion to distinguish them. Okay, so you have not a unique function, but you have a multitude of functions.
Hello. Thank you for the presentation. Here.
Okay, sorry, I didn't see you.
That's fine. So I actually see the semantic understanding being approached in mainly two ways. One is with the semantic web and ontologies and in rule-based ones, and another one is learning-based ones. So the problem with the semantic web in the rule-based ones is we have to define each and every logic in the whole world, that whatever we know of. And in case of learning-based ones, either it can learn by itself, either supervised or unsupervised, that's fine. Is there any particular area that shares the commonality between these two things, or that we can take advantage of the definity in the semantic web and the flexibility from the machine learning method?
Yeah, you can apply them, essentially. You can apply machine learning. I'm doing that. I have tools that apply classical machine learning techniques. Let's say boosting, take boosting. I don't know whether you know boosting. And what happens then? If I go back, let me go here. No, where was it? Here. Boosting allows you to build a classifier which is a weighted sum of weak learners. Each weak learner is specialized to do something, and then you can get here. This is a weighted sum. In fact, what I'm doing is that, exactly that.
Yeah.
So it's a combination. Essentially, you need to understand that when you build, for instance, in machine learning, a classifier for a class, the label of this class is an entity that you can use in the ontology.
Mm-hmm. Yeah. I kind of got that idea, but I mean something like, in learning, what if I want to explain, or what if I want to design what is an expensive hotel? Here it's actually easy to explain. Define a concept like a function or something. In semantic ontologies, we can have like has hotel, has price, something. But in case of learning, it's actually a difficult problem to deal with. So,
yeah, of course.
Yeah, that's what my question is basically. So how to have this functionality over there, or how can I use it? Or is there some development going on in that?
Let's say, let me see whether I understood it correctly. The point is here that is very, some notions were very clear at the very beginning of AI, which means essentially you have an upper layer in which you talk about your classes. I mean, conceptual things that you reason about. You can then usually redefine these classes in terms of more primitive classes. Mm-hmm. You go down, 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 and sooner or later you end up with what we call primitive classes, for which you don't give any definition anymore, and there you plug in a classifier.
Yeah, okay.
Which defines then numerically from a
okay.
training set what it means, let's say, recognizing a person in an image. Mm-hmm. And then you say, person for me is my primitive object. And then I can talk about being father.
Okay. Yeah.
Which is a person which has a child, which is at a symbolic level.
Yeah, thanks.
Okay.
Hi, Mike, here.
Okay.
So my question is, this is another method, and the topological question I'll ask maybe in the break, because there is a more mathematical. So the point is here, when you talk about the hazard means heavy rain, cyclone, and stochastic cyclone measurement, there are measurement already, like many companies also from the research point of view, many academicians are working on. So how you define from hazard, can you, with this process, can you build a hazard map? From that hazard map, we can then define a vulnerability curve. From there, we can deduce the loss function and everything. So do you see any motivation of work on this?
The usual,
mathematically, we can discuss maybe in the break.
Yeah, the usual way you do it, essentially, you don't introduce sharp borders in your definitions. Like rain, heavy rain, or let's say light rain. The human attitude is to define sharp borders for easiness or approximation of the real world. Say, okay, it rains 2 millimeters of rain per hour, and I define then this is light rain. The way to relax this approximation is just to find, technically, a triangular function around 2 millimeters. So let's say from 1.5 millimeter to 2.5 millimeter, it starts to be light rain. Of course, the closer you get to 2, the more the statement, it is light rain is true. The farther you go away, the less the statement being light rain is true. For storm is exactly the same. You just say not, okay, there is a certain amount of wind. No, you make a triangle function and you relax a little bit. And so you get intermediate cases like it's heavy storm or a light storm at the same time, and it's not a contradiction because you are in between, I mean, depending on the values.
Thank you very much.
Okay.
Yeah, suppose I have a multi-agent system. And a multi-agent system.
Multi-agent.
And each agent acquires its own ontology, fuzzy ontology. So I imagine the membership functions would all be different since it's contextual subjective. And now I want to ask a question of my team of agents. So here I want to aggregate the same concept and not different concepts. So what sort of operators would I use? And is this a kind of common technique used?
A good point, yeah. Suppose we look outside and say, oh, it's warm, and you, I don't know where you're from, but let's say, no, for me, it's cold. Or let's say, I'm Italian, and say, it's cold, and you say, you're, let's say, from north, and say, oh, it's hot.
Yeah, I'm from Sweden, so it's
from
very
Sweden,
warm.
So it's hot. I just came from Iceland, so we had in summer 5 degrees, so. Okay, so for you, it's hot, right?
Right.
How we exchange our notions, right?
Exactly.
Essentially, mentally, we are matching and try to find a compromise. First of all, I would like to try to understand what you mean with hot and what I mean with warm, right? But I assume that here, I did not touch that, so I don't know yet, so I'm guessing. There should be some arguments exchange between your information and mine, which means essentially, give me your function of hotness, and I give you my function of hotness so that we can understand each other what you mean with that.
Okay.
And then maybe we made just a kind of average or intersection, let's say kind of intersection.
Right. Yeah, this is a problem that comes up with distributed databases. So I'm just curious if you have the fuzzy.
Just simply among humans from different areas, right?
Yeah, and then so then the follow-up is what would be a notion of consistency if I've got this type of situation? Is there a notion of consistency?
Yeah, there is a notion of inconsistency because there are cases in which the situation is impossible. Even having the subjectiveness and context dependency, there are cases that it's just impossible, right?
Right.
Okay, it's weaker, but so.
Okay, thank you.
So technically, mathematical fuzzy logic is a kind of, let's say, technically paraconsistent logic, weakly. So it has also this small amount of small feature, but.
Thanks.
Okay.
Okay, thank you very much again for your talk and for the discussion. Let's thank the speaker again.
Thank you.